Hi guys. Oh, I didn't get water. I might have to go get water. Let me know in the chat if this is actually working. Yesterday's one, I did it, and it saved, but I didn't save in YouTube. I only saved on my computer, so I put it in as a video. So it is there, but it's just in a different section. What else? It is dark in here deliberately because about an hour ago my vision all went weird and I got a migraine, which is like the 5th I've had in 2 weeks. So I might be a bit dopey because of migraine and migraine medicine. But I wanted to try to do this anyway. If I feel too sick or anything, then obviously I'll have to go, but I did want to just check in with everyone, so I hope this is actually streaming. It is. Priya's here. Yeah, I did it, Priya, but I think because I'm using OBS Studio and I don't know, like obviously it's working now, but I don't know what I did yesterday, but it did record onto my Mac, so I uploaded it onto the channel, so it is there. But what I'm going to do today, because of yesterday, and as in you weren't there, and also because of this migraine, I'm just going to take it easy for all of us today. Do some consolidation, so you'll be able to go back and watch the one from yesterday, but this won't be a huge like leap forward. Okay, so our jobs this week are that we are doing a review of the first year mechanics and getting that to the point where you feel confident with it, and then we can build the second year mechanics super duper easily on top. And then also we are building our strong central pillar of differentiation, integration and trig. So practice, practice, practice. These things on the left, you just can't just learn them and do them. There's too much creativity involved and too much exposure needed. Whereas some of the other things we can just learn and do. So we're taking that into account, and we're doing a little bit of differentiation, integration and trig every single day or every single time I see you. This document reminder, we're going to be basically building up from the bottom because these are the things worth the most marks, but also I'm going to be leaning towards the right hand side because these are the things. I'm just going to turn this brightness down a bit because that's doing my head in. Yeah, the things on the right hand side take a long time to get confident with and good at, so that's the picture behind the pure. Alright, so the mechanics we're going to do today is to have another look at pulleys. So all pulley questions are F equals MA, so easy peasy to spot a pulley question because it's got a picture of a pulley and they are all the same 3 steps. So we're going to have a look at those 3 steps and give you a chance to have a go at some of them. Now, pulley questions often lead on to a SUVAT question, but as soon as they start talking about speed or distance or time, we've changed topics. We're not on F equals MA anymore. We'll be using this acceleration. We'll be using it down here in our SUVAT, but any part of the thing that's about how far it's gone or how fast it's going or how long it took to do something, that is moving away from F equals MA and into SUVAT. Okay, let's do our pure first. Okay. Test number 1. What are the 10 derivatives that you have to know? You only have to know 10, but you do have to know 10. So I'll give you a second to write those down yourself. I'll do it too, but I'll do it quietly. And I'll just wait until you've got started and I'll work a little teensy bit behind you, so hopefully you can test yourself on this. Oh, that one's a bit low. There they are. So, little things to remember: if it starts with a C, then it's a negative derivative. Otherwise it's a positive derivative, so that helps with remembering whether or not it's got a minus sign on the front of it. And then there's that relationship between tan and sec, where the derivative of tan is sec times sec, derivative of sec is sec times tan. Would we be asked to derive? Oh, that's an excellent question, and the answer is yes. So there's a video in TT, if you've got TT membership, there's a video in there called Proof of the Derivatives. That's a really good question. These are the ones that you could be asked to prove, okay? So you could be asked to prove sine and cos, but that would be from first principles. So you memorize the proof from first principles. And then you can be asked to prove any of the other trig ones using those two. So you can prove tan, prove sec, prove cosec, and prove cot by writing them in terms of sine and cos, and then using the quotient rule, or the product rule, or the chain rule. E to the x and 3 to the x, you don't have to be able to prove the derivatives of those. Or ln x, you do need to be able to prove, and this one you need to be able to prove using first principles, but you learned that in the first year. You actually do, have they asked you how to prove the derivative of a to the x ln a? I will check that one. That's the only one that I'm not 100% sure on, is the a to the x. I'll check that one, whether or not you have to be able to prove that the derivative of a to the x is a to the x ln a. But the rest, yes. So we will do that at some point as we go along. For now, just memorise, because the most important thing is the chain rule. Okay, chain rule. The chain rule tells us how to differentiate things where the x has been changed to something else. So the first one that we have is the one at the bottom. Something to a power. The half at the front, leave it at the front, just sits there watching. It's not doing anything, just sits there. What we have there is something to the power of 4. And the chain rule says, I know that that is not on our list, technically. Yeah, okay, well, why don't we go, hang on, let me put it here to remind me. Y equals a to the x. We'll go through the proof. I think I know the question mean. I think it was on an OCR paper. Okay, chain rule. So the chain rule says, do not worry that it is not x to the 4. Just do what you would do if it was x to the 4. So here's the half just sitting at the front. And then what I would do if it was just x to the 4 is I would pull down the 4 and I would change it to a 3. So that's what we do. Exactly the same as we would if it wasn't something more complicated. And then the chain rule says, but before you go, please now multiply by the derivative of the thing that wasn't an x. So the thing that wasn't an x, oh sorry, brain. The thing that was not an x is 6x squared, add 2e to the x. So we have to multiply by the derivative of 6x squared, add 2e to the x. But both of those are on our list, so that's all good. Derivative of 6x squared is 12x, and the derivative of 2e to the x is 2e to the x. So that's the derivative. And the hardest bit of the chain rule is recognising which of the 10 things you've got on the outside. That's the hardest thing. And then just remembering to use it. Okay, in this case we've got 6 ln, but it isn't ln x, but that doesn't matter, it is okay, we can use the chain rule. Ah, no Ronnie, that one. Okay, 6 is just at the front watching the proceedings, ignore it, leave it at the front. The derivative of ln is 1 over. Now we multiply by the derivative of the thing that was not an x. The thing that was not an x is e to the x plus e to the minus x, so that's what we're going to differentiate. So e to the x, the derivative is e to the x. E to the minus x, technically here I need the chain rule, because if you look down our little list here, e to the minus x is not on there, e to the x is on there. The derivative of e to the x is e to the x. But e to the minus x is not on here, so it's not an x, it's a minus x. So actually we need the chain rule here too. So we would differentiate it as if it was an x, so the derivative of e to the x is e to the x. So the derivative of e to the minus x is e to the minus x, but then we multiply by the derivative of the thing that wasn't just an x. So in this case we multiply by the derivative of minus x, and the derivative of minus x is minus 1. Now the faster you get at this, the less you have to write and the more you can just do really naturally. But for now you should be at the stage where spelling it out nice and slowly is really important. That derivative can be tidied up, but tidying up is not what we're focusing on at the moment, focusing on chain rule. Next, the derivative of 1 is 0, then a minus. The derivative of tan is sec squared. It's not an x, but that's okay, we just pretend it is an x for a moment. And then, because of the chain rule, we multiply by the derivative of the thing that wasn't just an x. In this case, the thing that wasn't just an x is half x. So the derivative of half x is a half. And again, all of these can be tidied up, simplified, made to look more pretty, but we'll come back to that later. What's important at the moment is practicing and regularly and getting used to and getting confident with the chain rule. Okay, let's see if I remember this question. Remind me if it was a different question or whether it just said prove that the derivative is this. Okay, oops, that's a bit low. There we go. I think the question just, I think it was on OCR, and I think it was just prove that derivative. Okay, so this is what we do. It's a little bit complicated. Yeah, it's a little bit tricky, this one. The trig ones are easier. This one is more difficult, but we're allowed to use this fact. We're allowed to use the fact that the derivative, do we even need it? Of ln x is 1 over x. I'm pretty sure that we need to use, but let's see what happens. So we're going to do ln to both sides. And why did we do that? Well, there's that lovely rule which allows you to pull powers down the front. Okay, now the advantage of this is that ln A is just a number. I'll put a bracket around it so that you can see. It is a number. It's a bit like having root 3 or, you know, like 7 over 2. Or so. Can you hear the rain? This big rain, and the sea is right there, and it's been really crashing today, which is lovely. Okay, so ln A, it's just a number. Imagine it as the number 3 or the number 7. Don't let it overcomplicate the situation, even though it looks more difficult and complicated than a number 7. It's just a number. Okay, now we're going to differentiate both sides. So we're going to differentiate that side and we're going to differentiate that side. Now, in the right hand side, imagine if it was 7x, the derivative would be 7. So if it's ln A, lots of x, the derivative is just ln A. So what I'm doing here is differentiating. Now I'm going to differentiate this. Now this is the step where I have to explain what's going on. This is the step. After this, it's going to be done in 2 seconds. Yes, with respect to x, exactly, with respect to x. And what that means with respect to x is that x is our variable that we are asking how much does this thing change as x changes. Now the derivative of 7x is only 7 if I'm differentiating with respect to x. And we always don't say that because we're lazy, and because we're almost always differentiating with respect to x, we just say differentiate, and we shouldn't really. We should say what we're differentiating with respect to. Now this, we have to do the same thing to both sides. We're differentiating both sides with respect to x. So how do we do ln y? We just use the chain rule. You may have seen this topic called implicit differentiation, but there's implicit differentiation is just the chain rule, because the chain rule says if you are in a situation where you have to differentiate ln of something, and that something is not just an x, it's something else, then don't worry, go ahead as if it was an x. Just do the thing. So ln x, the derivative is 1 over x. So ln y, if I differentiate that with respect to x, if I differentiate it with respect to y, it would be easy, it would be that. Oh my goodness, how many times can I choose the wrong colour? If I differentiate it with respect to y, the derivative of ln y is 1 over y. If I differentiate it with respect to x, then I need the chain rule. And the chain rule says, do it anyway as if it was an x, so the derivative of ln blah is 1 over blah, but then multiply by the derivative of the thing that wasn't an x. Now in this case, the thing that was not an x is this guy. So I need to multiply by the derivative of that guy. So on the left hand side, I used the chain rule. And from here, you just multiply both sides by y. And then you remember that from right at the top, we said that y was a to the x. So we can change that y there to a to the x. And we're done. Ta-da! So it's ln x. I knew there was one of them. It's ln x. You don't have to... I don't think you need to prove the derivative of ln x. Maybe we were e to the y is x. E to the y dy by dx is 1. Oh yeah, that would... No, it wouldn't. 1 over e to the y is x. Oh no, that does work, doesn't it? We could do that one. Okay, I'll just show you very, very quickly, just so that you've got those two proofs. Okay, for this one, I'm going to have to use the fact that the derivative of e to the x is e to the x. I will have to use this. So, y equals ln x. I'm going to do e to both sides, e to the. Now I'm going to differentiate both sides with respect to x. And on the left hand side, I'm going to have to use the chain rule because I'm differentiating with respect to x and it isn't x. So it's okay, we just use the chain rule. Okay, so on the left hand side, the derivative of e to the x is e to the x. So the derivative of e to the y is e to the y. But then I have to multiply by the derivative of the thing that isn't an x, and the thing that isn't an x is a y. So I have to multiply by the derivative of the y with respect to x. And if you differentiate the x with respect to x, you get 1, and then we can divide both sides by e to the y. Now if we go back up, it's not the first line, but it's the second line here. E to the y is x. So there we have our proof. If y is ln x, then dy by dx is 1 over x. But I did have to use the derivative of e to the x. Yeah. So let's go and correct that list. You need to know how to differentiate sine x and cos x from first principles. So that's a specific proof that you learn. Ow, my head. It's a specific proof that you learn how to do. Doesn't come up every year, but comes up a fair amount, worth memorising. Tan, sec, cosec and cot, you switch them into being sine over cos, or 1 over cos, or 1 over sine, or cos over sine, and then you use the quotient rule, which is how you differentiate fractions. 3a to the x we can do, and ln x we can do. I just showed you those ones. And the first year, first principles one is from the first year. Okay. Right. This is chapter 1,000,000 in the book, but it's the hardest thing in the A level. It's worth lots of marks, and it's really important that we start it now to build up that solid scaffolding that's going to hold the rest of it all together. Now, when we look at these integrals, we are trying not to think integration, because if you start trying to think, how do you integrate this? Oh my goodness, it is the most complicated thing in the whole world. What we're actually doing is we're thinking, what got differentiated? Now, sometimes we have to do work to get it into a form where we can say, oh, now I know what got differentiated. These ones we don't need to. These ones we can just look at and see what got differentiated. But as we move forward, we will see things where we have to do more and more work to get it to the point where we can say, oh, now I know how to do it. But all the ones that you actually do, the answer is this or this or this, or this or this or this, or this or this or this or this. Because one of those 10 got differentiated. 100% definitely, because they're the only 10 functions that you know. So let's have a look at this first one. Not obvious, I admit. There is nothing down here that if you differentiate it gives you something that has a square. Well, it's definitely not the trig. It's definitely not an exponential. It's not a fraction, so it hasn't come from ln. So was it a power? Let's write it slightly differently. So this is an example of the sort of work that you have to do. Rewriting things slightly differently to help your brain to see what got differentiated. Okay, you may be thinking, well, it's still not obvious, actually, what got differentiated. But because we know it's one of those 10, and we know it's not trig, and it's not an exponential, and it's not ln, because it hasn't produced a fraction, so it must be a power, that kind of gives you the in that you need. I'll leave a little gap at the beginning, but it must have been that. Because otherwise, how would I have got? If you think, try not to integrate, try to think something out of those 10, something got differentiated, almost certainly using the chain rule. Which one is it? If we end up having differentiated with something to a power, we must have started with something to a slightly higher power. But now I need to think this through. So now I'm thinking differentiation. What happens if I differentiate 1 minus x squared to the 3 over 2? Which numbers pop out that I don't want? So first of all, 3 over 2 would come down at the front, and then it would change to a half. And I do not want 3 over 2. See, there isn't a 3 over 2 there. It's not there. So I have to kill the 3 over 2 that kind of is going to come down. So it's pretty easy to kill it. You kill it like that. So down comes 3 over 2, cancels with 2 over 3, changes to a half. So that's all good. But it wasn't just x to the 3 over 2, it was 1 minus x squared to the 3 over 2. So actually, if I was differentiating this, I'd be using the chain rule. I would pull down the 3 over 2 and change it to a half, but then I would multiply by the derivative of the thing that isn't an x. And in this case, the thing that isn't an x is 1 minus x squared. So I would be multiplying by minus 2x. If I differentiate, I would be multiplying, I pull it down, take one off, and then multiply by minus 2x. Now the x I want, which is brilliant because I can't kill x's the way I can kill numbers. Numbers are easy to kill, but you can't just kill an x. You can't just put, oh, I'll put 1 over x, and then when the x comes out, it'll cancel. No, you'll see when we do the product rule that that is not, no, that doesn't work. Numbers though, because numbers just sit at the front, we can easily kill them off. So the thing I want to kill is the minus 2 that is going to come out. Do not want it, so kill the minus 2 like that. Plus c. And that's it. If you differentiate that, you get that. Let's try the next one. This one is a lot easier. So which of our things did we differentiate? Must have been that. Because that's the only thing that you differentiate and you get cosec squared. So now I have to think it through. So now I'm differentiating and I'm doing the chain rule. Perfect, minus cot, exactly. So when you differentiate cot, you don't get cosec squared, you get minus cosec squared. So there's a minus that I need to kill. It's very easy to kill a minus, you just put a minus on the front. And then when you differentiate, you get minus minus and they cancel, and that's why there isn't anything here at the front. What else comes out? So when I differentiate minus cot x over 2, I would get minus cosec squared x over 2. But, now remember, this whole time I'm differentiating, I'm not integrating, I'm not trying to integrate, I'm trying to work out what got differentiated. So I'm differentiating, I'm using the chain rule. So if I differentiate cot, I get minus cosec squared of x over 2, but then I have to multiply by the derivative of the thing that wasn't just an x. And in this case, the thing that wasn't simply an x is a half x. So if I'm differentiating, there would be a half, oh my goodness, I'm getting annoyed with myself now. There would be a half coming out that we don't want. Now I've managed to kill the minus sign. With a minus sign, I can kill the half using a 2. And that's the answer. Now the last one. Now the only thing that when you differentiate it, you get a fraction is ln. Now what we're ideally looking for if we have an integral with a fraction is this situation here. We are looking for a fraction and it's got something on the bottom and it's got the derivative of that thing on the top. That's the ideal scenario, because if we see that, then we know exactly what got differentiated. It's ln of the bottom. Now if the derivative of the bottom wasn't on the top, we'd have to do some more thinking. And there will be fractions like that and we will have to do some more thinking. But if the derivative of the bottom is on the top, then there is no thinking involved, which is great. It's just ln of the bottom. Okay, now let's do the differentiation and the chain rule to see if there's anything we need to murder. Ln x squared plus 4 goes to 1 over x squared plus 4. But then we have to multiply by the derivative of the thing that wasn't an x. If it's just an x, then it's fine, it's 1 over x. If it isn't just an x, then after we've done the 1 over, we now need to multiply by the derivative of the thing that wasn't an x. In this case, the derivative of x squared plus 4 is 2x. So this 2 that's coming out, I do not want, so I'm going to kill it. Now there's also this guy. That one's just sitting at the front watching. That one's just a multiplier. That's just making my function x, or my expression x over x squared plus 4, it's just making it 3 times bigger. It's just watching. Just like when we had these ones and we were differentiating, we had this guy just watching, sitting at the front, not doing anything, not causing any trouble, and the 6 was just sitting at the front, and the minus sign was just sitting at the front. They're multipliers, they don't affect the actual differentiation process. Exactly the same with integration. So that 3, I don't even need to think about him at all. He can just sit at the front. The half is there because I'm killing a 2 that would come out because of the chain rule. And now it works perfectly. So whenever you see a fraction, check that the bottom, if you differentiate it, is on the top. Not worrying about numbers because we can kill off numbers. Yes, so this is a really good question. This comes with practice, and the thing is with this is it only comes with practice. So if you look back at the chili rating, the stuff on the right hand side, these are the things that everybody needs to keep coming back to. And the things at the bottom are the things worth lots of marks. The things on the left hand side you can learn really, really quickly, but the things on the right hand side, they require this constant little drip feeding of this coming in. So that's what I'm always going to be doing with you in these sessions all year, is a little bit of trig, a little bit of differentiation, and a little bit of integration, and then slowly you will build up the skills. And I'll introduce new ones now and again, but it will just mean that you don't have to have that responsibility or worry. By the time we get to March, you'll be really good at integration and really good at differentiation and really good at trig. And there won't be a day where that happened. Whereas the other topics like modulus or approximations, we could have a day and I could teach you it and we fix it and then it's all right. But these topics, the differentiation, the integration and trig, and particularly those 3 chili ones, they require everyone to just slowly practice. So what I would encourage you to do is either come to these lives or watch the recordings and just have a go with it yourself rather than waiting for me to do it. Oh, that is a very good question. You're full of good questions today. Okay, the reason that this is on the right hand side is that, so the right hand side is not things that are difficult. It sort of is. It's things that take a while to become confident with. So there are things on the right hand side that take 1 second to teach. 1 second. But that doesn't mean that if I then chuck a question at you, you would be able to get 4 marks. And one of the things with the modulus that is a nuanced, like a little weird thing with the modulus, is that when you learn it, you're like, oh, this is fine. This is all right. Yeah, I can do this. This seems fairly straightforward. Then, when you give students an exam question, cannot get it right. The other thing that's in the same category is the solving trig functions from the AS. So, like, I don't mean like where it's got sine squared and cos. I mean literally just sine of something is something on a particular interval, or cos or tan. These are things that if you ask students whether they need to learn it, they'll say, no, I've learned that. Yep, I use the whatever method, the graph method or the cast method. But yeah, I know how to do that. But give students a test, like a proper test conditions, the answers won't be right. They'll be sort of right, but it won't be full marks. So trig, basic trig equations and modulus come into that category where until you try and do it all by your very own, you don't realise that actually it takes more thought than you thought, if that makes sense. But you're right, it's not a difficult, there's not a lot to learn in there. And it is just straight lines, you're completely right. Okay, so we've already introduced the reciprocal trig functions. If you look at the third letter, that's the one that will tell you what it's the reciprocal of. So if you ever forget, sec, third letter is C. Cosec, third letter is sine. Third letter is sine. Third letter is S. Cot, third letter is tan. Sec and cosec and cot are not worse than sine and cos and tan. The advantage of sine and cos and tan is that we have sine and cos and tan buttons on the calculator, so we can solve sine x is something and cos x is something and tan x is something. If you have sec x is something, or cosec x is something, or cot x is something, we'd have to flip them because we don't have those buttons. But other than that, they're of equal use and equal importance and equal niceness. So it's not that they exist purely to be a pain in the neck. They are really useful functions, and it's nice and it's cleaner to have those than to always be writing 1 over cos or 1 over sine or 1 over tan. You'll get never really 100% happy with them, but you'll get more and more confident the more you use them. Same as with the integration, takes a while. Okay, we introduced yesterday, when I wasn't live streaming, but I did record it, one of the Pythagorean identities. We've got 3. So we already know from the first year, sine squared x plus cos squared x is 1. Opposite each of the sine and cos and tan, put its reciprocal. So opposite tan squared, I'm going to put cot squared. And opposite cos squared is sec squared. And opposite sine squared is its reciprocal, cosec squared. And then if you put that arrow the same shape on the other 2 spaces, then what you have is your 3 Pythagorean identities. And it really helps not to use this hexagon so that you don't get muddled on where the +1 is and what's what. So your Pythagorean identities are sine squared x plus cos squared x is 1. 1 plus cot squared x is cosec squared x. And tan squared x plus 1 is sec squared x. And you can see on the bottom here, it's probably going to be useful to use that Pythagorean identity. Okay, so this one isn't a proof, it's just to simplify. And I am going to, actually no, I'm not. I was going to say I am going to change them into sines and coses, but I'm not yet. Because if I use that Pythagorean identity on the bottom, then that happens very nicely. Okay. Now I'm going to do something which we teach the first years. You get sine squared theta cos theta. Oh, I might get that too. Yeah, let's see. What I'm going to do is and you use this in the proof of the derivatives as well, I'm going to slide them apart so that I can see them individually. So what I've actually got here is cot theta multiplied by 1 over cosec theta. And if you think of it like that, you can see that the top is cot theta times 1 and the bottom is cosec theta times 1. So I haven't done anything really especially clever, but it's allowed me to isolate or think differently about what I'm looking at. Instead of thinking of it as a fraction, I'm thinking of it as a product. Now, in the same way that cosec theta is the reciprocal of sine theta is the reciprocal of cosec theta. So I get cot theta sine theta. Now, I don't have to leave cot theta as cot theta. I could change it to cos theta over sine theta. Oh, hang on a minute. Now look what's happening. Because cot is the reciprocal of tan, and tan is sine over cos. So cot is tan upside down. And now this happens. So the whole thing boils down in the end to just cos, unless I went wrong. Unless I went wrong somewhere. What do you think? Now, this is a good one for demonstrating that sort of the knee-jerk going, I must get rid of all reciprocal trig functions and change everything into sine and cos and tan immediately, is not a good way to go. So that's the main message from this. There's two main messages. One is, oh no, yes, I am the expert in terms of like knowing the spec, and I used to write the mark schemes. So yeah, I know how the exam system works and all the spec and all the maths, but can I add up? No. Can I like do maths without making a silly mistake? No, because I have a human brain. So it is very likely that somewhere down there I might have done something silly. So do question everything that I do. I think the important things are, number one, it's not that sec and cosec and cot are bad. So they are your friends. Oh, so that's in the way. They are your friends. They are not horrible. Yes, definitely there are times when we want to write things differently and write them in terms of sine and cos and tan, but it might be the other way around as well. We might want to change something, instead of like sine, we might want to change it to 1 over cosec, depending on what we're doing. The other thing that I think is important on here, or useful on here, is this step here that I did, because you're going to use that in the proof of the derivatives, and you're also going to use it a lot of times when you're doing trig proofs. And what I did was to take a fraction and to turn that fraction into a product. Not turn it, but think of it differently to allow me to simplify more effectively. So the abstract idea would be that if I have A divided by B, then that is the same as A multiplied by 1 over B. It's a relatively simple concept, and yet we don't think to use it very often, and it can be really, really helpful in trig proofs. So unless anyone has spotted a mistake, then I think we're okay with that one, and we will try this trig equation. So we're going to be using our Pythagorean trig identity, and it's going to be that one. Okay. If you haven't learned about radians yet, do not worry. The only difference between doing this in degrees and doing it in radians is that our calculator is going to be in radians. That's it. Everything else that we do will be absolutely identical. Okay. We want to use that relationship between tan squared and sec squared. Tan squared plus 1 is sec squared. So if I just have tan squared, I can change that to sec squared minus 1. So just like in the first year where you replace sine squared with 1 minus cos squared, or you replace cos squared with 1 minus sine squared, we're going to replace tan squared with sec squared minus 1. Now these questions, oops, I changed the angle. It's a half theta, not theta, it's a half theta. Now these questions that use the Pythagorean trig identities, they don't come up anywhere near as much as you think they would. In the first year, you've only got sine over cos is tan, and you've got sec squared is 1 minus cos squared, sine squared is 1 minus cos squared, and cos squared is 1 minus sine squared. That's it. So if you get a trig proof in the first year or a trig equation in the first year, pretty much all of them are replace sine squared x with 1 minus cos squared x and then you have a quadratic, or replace cos squared x with 1 minus sine squared x and then you have a quadratic. Now the same is true in the second year, although there's 3 possibilities because we've got 3 Pythagorean identities. Replace that with that, now you have a quadratic. But when you actually look through the papers, this doesn't actually come up that often, which is a shame because it's the easiest of all the trig identities. If we go back to our chilies, Pythagorean identities are on 2 chilies, whereas, and this is the biggie, double half. Double half angle comes up all the time in lots of contexts and it is hard. Whereas the Pythagorean identities and the addition formulae, they're not too bad. I mean, you need a little tiny bit of practice, but then really not too bad. It's the double angle formulae that cause the problems. And when you look through papers, it's the double angle formulae that they're putting in time and time again in various different places in the paper. So yeah, we do need to practice this, but when we get there, double angle formula is going to be the one that we need to keep practicing and practicing and practicing. So I have replaced my tan squared with sec squared minus 1. Everything else is going to stay the same. And then we can tidy this up a little bit. And now we have our quadratic. How do we solve quadratics? Factorize or formula? I can factorize this one really easily because it has a common factor, so that's going to be super easy. So as soon as you see that quadratic, instead of thinking, now what shall I do? Think, I know that there are only 2 ways I solve quadratics, factorising and the formula. I don't put things on the right hand side and divide. That's not a method for solving quadratics. Quadratics are solved by factorising or using the quadratic formula. And this one is easy to factorise. Okay, so we get 2 equations to solve. That one and this one. But as I said earlier, we do not have a sec button on our calculator, so we're going to flip them both upside down. Now, the one on the left. Yes, that is a good idea. So one of the things that you can do when you see a quadratic, but it's basically a hidden quadratic, then it sometimes really helps to simplify it by introducing a new letter and saying, right, wherever I see sec theta over 2, I'm just going to put a p. And then it's much cleaner, it's much more obvious how to factorise it. And quite often I will do that. It depends whether I can see how to factorise it or whether actually it's all getting a bit overwhelming with the amount of letters and numbers and stuff, and actually if I use that p, it will really help me to see the quadratic and factorise the quadratic more easily. So absolutely fine to do it, good idea to do it, not necessary, but if you did, you would get to this same point and then you would say, oh yeah, but p is sec a half theta, so actually I need to solve sec a half theta is 0 and sec a half theta is 2. Now sec a half theta equals 0 doesn't have any solutions because you can't do 1 over 0, you get infinity. There are no solutions. So I'm going to go back and say no solutions. And I'm going to write why there's no solutions, because this is a mark, and this is a mark that most students drop. The students that get this mark are the ones that have either studied mark schemes, like studied them to see the real detail, or people who've had teachers who are examiners or who have studied the mark schemes and understand all of the little details, marking their work and telling them, oh, you drop a mark for that. So when you have a solution, or you have a route that comes out that looks like it leads to some solutions, but actually there aren't any solutions, instead of just ignoring it, we have to say why we're ignoring it. Now this has got no solutions. Why has it got no solutions? Because the graph looks like this. That's what sec x, let me move it up a little bit. That's what sec x looks like. Sec x does not exist between 1 and minus 1. This is 1, this is minus 1. And if you are trying to solve sec x equals, and it's something between those, so like this bit, this bit, this bit, like we were trying to solve sec. The sec of something is 0. Sec of something is never 0. It's either 1 or something bigger than 1, or it's minus 1 or something less than minus 1. And the thing that you're looking at there, the topic, is range and domain. The range of a function is all of the possible y's that it could equal. And you have to look at the graph really to see what the range is. So for this one we would say that the reason that sec of something is 0 has got no solutions is because the range of sec x is all of the y's less than or equal to minus 1 or bigger than or equal to 1. And that, I mean, we don't need to worry. It's November. We really don't need to worry at the moment about these little tiny marks. But I'll just keep reminding you of it. Don't ignore a potential route. Explain why it's got no solutions. Y is less than or equal to minus 1, or y is bigger than or equal to 1. Or you could use sec x instead of y. Okay, the other one we can solve. Now that is a test for you. Can you solve cos of a half theta is a half on minus pi pi and get all of the correct answers? Okay, I'm going to do it, but I'm going to do it without talking, and I'm going to do it using the method that I showed you yesterday and the day before, which is just so much better than cast and graph. So much better. Okay. Okay. Yes, I got 2 as well. I got 2. 2 pi by 3 and minus 2 pi by 3 are the 2 answers. So if you would like a really easy way to do this, notice I didn't do graph, I didn't do cast method, I didn't have to worry about that domain until I got right to the end, and then I just had a look at them. The only thing that I had to memorize is how to get from there to there, and I used the fact that it was cos to get from the first solution to the second solution. And then I just took 2 pi off and added 2 pi on, and took 2 pi off and added 2 pi on. And that works for sine or cos or tan. So you don't have to have all these complicated different ways of thinking about sine and cos and tan. The only difference between sine and cos and tan is how you get the second solution. If it's sine, you do pi minus what you got off the calculator. If it's cos, you just stick a minus sign on what you got off the calculator. And if it's tan, you do pi plus what you got on the calculator. And other than that, the method is always exactly the same, and yeah. So it's always 360. If you do this method, then it doesn't matter whether it's sine or cos or tan. You get that one from the calculator, you get that one using the rule, and then same for sine and cos and tan, take off 2 pi, add on 2 pi, or if it was in degrees, take off 360, add on 360. So very little to learn and very little to memorize, and you don't have to think, which is just the best, to not have to think. Okay, last thing for today is having a look at some Pulley questions, which I did go through yesterday, but I want to take it a little bit further. So there are 3 steps to all Pulley questions, and the 3 steps are: number 1, draw force diagrams; number 2, do F equals ma; and then number 3, do simultaneous equations. And that will answer any Pulley question. First year Pulley, second year Pulley, all of it. We don't even have to read it. That will be what you need to do. Diagram, F equals ma, simultaneous equations. Now the diagrams for these sorts of pulleys are super duper easy. You've got the weight, you've got no normal reaction and no friction because there's no surface. You've got the tension in the string, and that's it. So just weight and tension, and that's it. So really, really simple force diagrams. F equals ma is always done in a line. Okay, F equals ma is always done in a line. So it's all the forces under a particular line. Now, how do we know whether the t is positive and the 3g is negative, or the t is positive or the 5g is negative? Which one's positive, which one's negative? You need to know which way it's accelerating. So with this one, because q is heavier, q is going to go down. So this one is going to accelerate down, which means I'm going to take the 5g as positive. Whereas the other one, p, that's going to go up, which means the t would be the positive thing. And when you've got that idea of all, my F equals ma is all the forces under a line, and anything that's pointing in the direction of the acceleration is the positive thing, then the F equals ma's come out really, really easily. So for this one, it would be t is positive for the first one, equals the mass times the acceleration. And then for the next one, 5g is the one pointing in the positive direction, equals the mass times the acceleration. And then you would do simultaneous equations on these two. Make one of them say a equals, stick it in the other one, or make one of them say t equals and stick it in the other one. Same deal. With this one, we've got 3m and 4m. This one's heavier, so that one's going to go down. That one's going to go up. So with the first one, it will be the 4mg. Oh my goodness. It will be the 4mg that's positive and the t that's negative. mass times acceleration. For the other one, it'll be the t that's positive and the 3mg that's negative. Mass times acceleration. And then simultaneous equations. And all of these ones, these first year Pulley ones, where they're dangling down, are going to look the same. The only bit you need to think about is which way those arrows go for your F equals ma. Which one is going down and which one is going up. The heavier one will go down, which makes those forces positive and the other ones the negative. Now what gets a bit more tricky is when we introduce more directions. But it's still true that we're going to be doing F equals ma. So we're going to be doing F equals ma under there, and we're going to be doing F equals ma under there, and we're going to be doing F equals ma under there. And then we'll have 3 F equal ma's, and we'll do 3 simultaneous equations to find the stuff that we're interested in. So which way they're going to go? The crate is going to accelerate up. So the t will be positive and the 300g will be negative. T minus 300g is the mass times the acceleration. The blue one, the car's accelerating that way, the van. So it will be 5,000 minus t minus 780 equals the mass times the acceleration. But there's a third one, which is this one. Now this is not accelerating at all. It's not accelerating up and it's not accelerating down. It's moving across. It's not even moving up and down, let alone accelerating up and down. So for this one, for this direction, for this F equals ma, a is 0. But we're still using Newton's second law, even though you could think of it as Newton's third law, that there's an equal and opposite reaction, or the resultant force is 0. There is no acceleration, so there is no resultant force, because acceleration comes from a resultant force and a resultant force creates acceleration. So if there's no acceleration, there's no resultant force. All the forces balance. So F equals ma, instead of writing r minus 1300g equals 0 or 1300g minus r equals 0, we can just do it as balanced forces. All the ups equal all the downs. But it is still F equals ma. So for this we would get 3. We get the one for the crate, which is being pulled up, we get the blue one and the red one, and then we do 3 simultaneous equations to get all of the things. And that's going to be the same with all of these ones. We're going to have 3 F equal ma's. This one, and this one, and this one. For the blue one, a is 0, so it will be r is 2.5g. And whether or not the b goes down and the other thing goes right, or if there's a force pushing the one on the table left, maybe the one on the table would go left and the one hanging down would go up. So we do have to read the information a little bit to see what's going to happen. In this case, the one on the top is going to go right, the other one's going to accelerate down, so t will be positive and the 12.7 will be negative. F equals ma, F equals ma, F equals ma, simultaneous equations. The other thing that you can see I've highlighted on these is how I know that the t is the same as the t and that the acceleration is the same as the acceleration. Because when we do F equals ma, simultaneous equations, the reason we can do simultaneous equations is because they've both got a t in and they've both got an a in. Now why are they the same t and the same a? It's because the pulley is smooth and the string is inextensible. And if you have a look at all of the questions, they are going to say that the pulley is smooth and that the string is inextensible. And that is how we know that the T will equal the T, the tension in the string will be the same either side of the pulley, and the acceleration will be the same, the inextensible string. So 99.9% of the time, you're going to see those words, smooth and inextensible. I found one where it's slightly different, this one. So, smooth peg. Fine, it's a peg, not a pulley, whatever, pulley, peg, same thing, smooth. So, because it's a smooth peg, that will mean that the tension is equal to the tension. So this tension is equal to this tension. But when I do my F equal MAs, can I put the acceleration equal to the acceleration? Well, nowhere on here does it say that it's an inextensible string. It says that there's a box, it's on a shelf, the shelf is rough, that's why there's some resistance to the motion. Doesn't say a single thing about the string. But it says this. The inextensible string would be the thing that allows us to use A equals A. So F equals MA, that A, and F equals MA, that A, are the same. Now this one doesn't say it's an inextensible string, but it does say that they have the same acceleration. So now it's okay. Now I can use A the same as A, and I can use T the same as T because they told me that it was a smooth peg. Now this question says in part D, can you see part D? There. State one assumption that you have made. State an assumption that you have made. Now this is a really unusual question because normally they sort of give you it on a plate what you're supposed to say, but there's lots of other assumptions that we need to make when we're modelling this to mean that the method that we are using every single time is going to work. So what we'll look at, not now but later, is, because these are only worth like marks, hardly any, we're going for what is the biggest mark, and the biggest mark in a mechanics paper is the connected rate, the connected particles. Diagram, F equals MA, F equals MA, F equals MA, simultaneous equations, always. But when we come to it, we will look back at all of the other things that they tell us in these questions. So they say it is a fixed pulley. It's always a fixed pulley. Why does that matter? It's a smooth table. Or maybe it's a rough table. What does that matter? And the balls are modelled as particles. What does that let us do? The rope is light. What does that let us do? The pulley is small. What does that let us do? So there are all these things, not as key as the inextensible string, acceleration is acceleration, smooth pulley, T equals T, tension equals tension. But there's all these other little modelling things that we need to be aware of and know why they're there and what they're telling us, which means that then when they ask us a question about that, we can pick up that extra little mark. Okay. In terms of the mechanics, going back to the beginning, we are this week doing a review of all of the first year mechanics to hopefully give you the confidence to then build on that into the second year mechanics. I'm going to consider pulleys done, although I understand that you might need a bit of practice with the force diagrams, or you might need a bit of practice with the simultaneous equations. They can be nasty, but the concept is there. If it's a pulleys question, diagram, F equals MA, F equals MA, F equals MA, simultaneous equations, that will always work. There is other F equals MA questions which are more abstract, or they're not about connected particles, so we will do another session on F equals MA, but next we'll move on to variable acceleration, which will only need one session to go through. And then slowly over the next week we will cover the whole of that mechanics, and you will feel super strong with the mechanics. We can try doing mechanics papers and you'll see that actually there's only 3 questions. F equals MA questions, variable acceleration questions, and constant acceleration questions, and that is it. In the second year, there's a fourth one called moments. But in the second year, there's only 4 types of mechanics questions, and in the first year, there's only 3. Okay, I'm going to have to leave it, guys, because my breathing is starting to get bad again. My headache didn't come back, so I caught it early enough with the Mig Relief, thank goodness. Thank you so much for coming to see me tonight and for doing some maths with me. I'm not going to do Fridays or Saturdays because who wants to do studying on Fridays and Saturdays? So I will see you next on Sunday.